delta, this type of framework. So we're going to try and dynamically replicate the option position by taking a long position in the stock and seeing what are the outcomes under different scenarios. So the starting point here is we're going to take the values as presented at the option in the initial parameter values as given here. So stock price of 100, K 100, or 5%, no dividend yield, volatility 20%, and time period 52 weeks. So we go back into our spreadsheet and we say, okay, let's simulate a stock price. And we want to do that for a 52-week period. So let's take this, remove this, and take this away. So we go 23, 24, right down to 52 weeks. Okay, and maybe we can remove some of these cells here. So delete, and we've made a little bit of space. So our starting point would be in week 0, when the option is set up, stock price is 100, exercise is 100, risk-free rate 5%, dividend yield 0, 52 weeks, and 0.2. So to work out the value of the option, we could go into, so we could think of the value of the call, just simply call time value from Black-Scholes would simply be equal to, let's get the formula from Visual Basic Editor. Could just take this and copy, go back in, and we could say home paste, and then we can say equal to, and then link back. So the stock price is 100, K is equal to 100, the time period is equal to, now we could say this divided by 52. We could take the risk-free rate as being a given of 5%, dividend yield is 0, and the volatility is equal to 20%. Okay, so if we're correct, then the value of this should be 10.4. Should be, for a call option, should be 10.45. Okay, so we're getting that value, and that would suggest their results are relatively okay. Now, so 1 week passes, and then we're down to 51 weeks, and then another week passes, and we go all the way to time period 0. Okay, so 52 weeks passes, no more time left. So the time remaining is falling all the time as we go through this. And if we were to work out the value of delta here, again we can go back into the developer tab, and again it's important that we get the delta C. So in fact what we could do is these values are in the same order as they call S, K, T, T, R, Q. So just remember delta C. So let's say equal to, let's take this, just copy, paste, put the equal sign in front, getting the same value, fine, and instead of saying BSM whatever, we'll say delta capital C, and we've been prompted already for that. Okay, and the value of 0.63, which if we check is the same as what we had before. So when we worked out the value of the call, when we took it as being 1 year and same parameter values 1045,058. Okay, same as here. And then for the delta, where I worked it out as delta C, okay, 6368. So we have 6368. So initially what we should do is how many stocks should we buy? Because remember, the nature of this strategy really is to discover, really is to give, to know how many stocks should we go long if we had shorted 100,000 call options. So if we go back to our spreadsheet, we can put in here somewhere the value of our initial number of short calls, and we must specify a value here. So let's say 100,000. Okay, so we'd say how many stocks should we buy? The number of stocks we should buy is equal to 0.63683 by 100,000, and we'll F9 that. So our initial position is we should buy 63,683 stock, and of course the cost of that will be this multiplied by the cost of the stock, and the cost of the stock initially at the setup is 100. So it's 66,368,000. And we could say, okay, the cumulative cost is going to be the same as, we don't really have to worry here about interest for the moment, but the initial cost here is just this 6.368 million. And the interest cost we also have to take into account, because money tied up in the purchase of the stock is money that can't earn deposit. And we've said that the risk-free rate is equal to 5%. So let's model that. The 1 week interest cost, we might say, is equal to the sum of money borrowed, and then we multiply it. We'll take the continuously compounded rate, so we multiply by EXP open bracket the rate of interest, which we've put here as 5%, F4, multiplied by the time period, and it's weekly, so this is 1/52, and we'll check that again in a moment. Okay, so F4 that as well, and then we subtract away the sum, the principal. So our interest cost is 6,126. So just to check this, it's the principal involved by ER and then T. And what's T? T is this DT, which is just simply 1/52. So it's for a week. It's an annual rate, and then the weekly cost is equal to the principal with the interest minus the principal. So that's the weekly cost of borrowing that sum of money. Now we've generated, if we go back to my YouTube site, I did a stock price simulation tree. I outline here how you generate or how to simulate a stock price. Likewise, I set up the same here. So basically, if I hit F9 here, this will update. And what is basically here, what I have here is an implementation of this. So we set out a value for the drift, and the change in the time period is 1/52, and then epsilon is the norm's inverse rand, and then the volatility is equal to the time period is C2, so that's the change in the time period, and we're scaling by the volatility C3, which is the same as the values that we have here. Okay, so we could, if we liked, change this value here equal to the 0.2, and we'll F4 that, and Black-Scholes assumes constant volatility. And we could also assume that the dividend yield here is equal to this value here, 0, so F4 that. And we could also assume that the risk-free rate here is not a constant, it's equal to 0.5, which is this value here, and F4 that to lock the cell reference. And the 100 is locked, okay, and this value here is equal to our value here at F4 that. Okay, so if we change something here, it will reflect down here. The only thing that is constant here is the 100 and the exercise, so we can leave that as it is and make changes later on. Okay, now so we have a simulated random stock price that adheres to geometric Brownian motion. I want to, the volatility is not going to change, so I could pull these values down. Okay, we pull these values down. That value's got 52. Okay, so where possible, I just pull these values down. 0.5, that's not going to change, and I'll do the same with the others. So I'll keep pulling these values down. So here I go again. So I've generated a simulated stock price, and if I F9, that should update. So what have I done wrong? Anything? No, it looks okay. Does it? Let's see. 83, 87. Okay, looks like it's okay. And I'll pull the volatility down as well. Okay, so these values are constant. So next thing I need to do is to S63, where does that come out of? 63,000 is the product of the delta equal to delta delta times 100,000, the number of short calls that we initially started out with. So that's 63,000. That's the price by the number of shares we had to go long, and this is the cost. So let's just take these three together. Let's take these two together. No, delta. Let's just generate delta by itself. Okay, and the value, and now this is we need, it's not 0, we have to put in a value that's really, really low, but not 0. So a value here actually emerges. Otherwise, time periods, if we set t equal to 0, Black-Scholes is not implemented. Okay, so we've dealt the values, and now the number of shares purchased is 63,000. And just by returning, I've actually changed the spreadsheet. But to work out the rest here, to complete the rest of this delta hedging type strategy, I'll need a bit of time, so I'll do that in the next video clip.